Greetings everyone, I'm James Capuli from DST Pagasa, and I'm here to share with you the results from our recent study pertaining to a tornadic event in the Philippines, particularly with the environment and features associated with the storm. So let me dive first with the idea that tornadoes occur worldwide, excluding Antarctica, and the Southeast Asia, particularly the Philippines, is no exception. Recent studies have identified distinct tornado hotspots in the Philippines, a tropical country, confirming that these events are not just random gusts, but organized severe thunderstorm-driven phenomena somewhat comparable to classic supercells observed globally. Now, as a quick refresher to everyone, thunderstorm initiation requires three key ingredients. We have moisture, steep lapse rates, and a lifting mechanism. But sustaining thunderstorms, especially supercells, requires vertical wind shear, which tilts and organizes the updraft. Subsequently, tornado genesis demands yet another step, the ingestion of ambient horizontal vorticity, its tilting into vertical, and intense stretching by accelerating the updraft, dramatically amplifying low-level rotation, just like what you're seeing right now, the Enderlin, North Dakota EF5 tornado, which is a byproduct of that process. Now, this idea materialized on the 27th of May 2024 when a tornado struck Arayat, Pampanga around 04:50 UTC, damaging over 50 homes. Footage that you're seeing right now is the development and the intensification of the tornado. And ground reports confirm this tornado with a clear wall cloud and a mesocyclone. Now, this event provided a rare chance for a severe weather analysis in the Philippines. For our methodology rather, we are using the Era 5 reanalysis. We also gathered soundings, both modeled and observed soundings from Sounder Pipe, Himawari 9 satellite data from TREDS, Subic radar, which is a S-band radar, plus the lightning data from the Estipal ASA, the Weather Bureau of the Philippines. From there, we reconstructed the storm environment. Let's start first with some visual confirmations. The Arayat Pampanga tornado manifested itself as a multiple vortex tornado with a clear wall cloud, a missile, and a mesocyclone stacked on top. The tornado damaged several houses, flew roof structures, damaged several wooden and concrete electrical poles, which at one point earned a negative rating. Synoptically, despite the presence of tropical cyclone Ewinyar to the east, Luzon, particularly central Luzon, was largely cloud-free, promoting strong surface heating and boundary layer destabilization. The mid-level geopotential heights, or the 500 millibar heights, suddenly lowered, and early season southwesterlies transported deeper moisture, which eventually led to the initiation of the convective storm. You can actually see this through the Himawari 9 satellite imagery. This is supported by the ear-fied cross-sections around all 5 UTC, which showed strong low-level instability. We have enhanced convergence as well, vigorous upward motion, and a sufficient background vorticity, further modulated by local terrain influences such as the plain-to-mountain flow. Convectively, the environment in Luzon where the area of interest is located is primed for explosive convection to occur. We have steep lapse rates, ample instability, and bulk wind shear in the lowest 6 km, and even composite parameters such as the WMAP shear approaching in the upper 900s. This is supported by the 05 UTC sounding in Era 5, steep lapse rates, and the depth of moisture extends to around 750 hectopascals, which translates to high 3 km cape, high total mu cape of more than 3,700, and E cape of around 2,500. This is indicative of a stout updraft capable of withstanding entrainment and dilution. While low-level shear and storm-relative winds were quite weak, strong 0 to 6 km bulk shear and highly streamwise vorticity, as seen in the storm-relative hodograph, enabled efficient updraft ingestion and stretching. Now, both satellite and radar data confirm a maturing supercell. Cloud tops colder than -70 to even -80 degrees Celsius, intense overshooting, and a semi-discrete cell within a larger storm cluster. We also found nearby auxiliary cells in parent storm's flanks, conditions known to favor that tornado genesis. You can see high reflectivity values of more than 50 dBc rather. We also have sign of rotation couplet seen in velocity scans. Close inspection, particularly radar cross-sections, suggested a bounded with echo region, a tilted updraft thanks to the ample bulk wind shear, and greater than 50 dBz reflectivity course. Meanwhile, velocity scans showed a tightening mesocyclone evolving into a clear velocity couplet by 0450 UTC or the 1250 LST, local standard time. We also have lightning data, which revealed a pronounced lightning jump exceeding 170 flashes prior to intensification, followed by pulses consistent with observed evolution and tornadogenesis. Most of the flashes occurred within and below the mixed space region, or the 4.5 and 5.5 kilometer. And the storm produced predominantly positive polarity lightning, similar to other significant tornadic supercells such as Spencer, South Dakota F4 event in May 1998. So just to summarize to you what we discussed, the environmental conditions, particularly the synoptics first, shows that the storm evolved in a semi-discrete to discrete mode. This was largely driven by the subtle lowering of geopotential heights in the mid-levels, and crucially the influence of local terrain, specifically the lee side convergence near a mountain, provided the necessary dynamical forcing to initiate lift. A low-level monsoonal flow acted as a fuel source, pumping moisture over central Luzon or Luzon landmass. When we look at the convective parameters, the environment was primed for explosive growth, with cave values exceeding 3,700 and steep low-level lapse rates, while low-level kinematics lagged behind, particularly the low-level shear and storm inflow. Both deep layer shear was modest at 20 knots, and the vorticity near the surface was highly streamwise, over 80% at times, creating an environment favorable for tornadoes. Now, moving forward to our remote sensing analysis, the data confirms the severity of the system. Radar imagery revealed classic tornadic signatures backed by satellite imagery from Himalayan line, showing cold anvil layers and overshooting tops, indicating a powerful updraft. Interestingly, we found that auxiliary cells forming along the storm's rear and left flanks likely played a major role in the storm's intensification and subsequent tornadogenesis. We also noted a distinct surge in lightning activity which correlates with the presence of active cloud hydrometers and updraft intensity. So moving forward, our recommendations to better anticipate and analyze such events include usage of dual polarization radars to identify tornadic signatures, such as a ZDR column and KDB arc, applying convection allowing models or CAMs to resolve these localized terrain effects, and utilizing advanced remote sensing techniques to quantify damage more accurately in the aftermath. So that actually ends my presentation. This is my first time presenting in a blockbuster international conference as KGU. I hope you learn a thing or two. And here are my references. Maraming salamat. Thank you.